Ganon po. करना चाहता हूँ।
Yeah, so very good morning, dear participants. I welcome you all on the second day of AICTE ATAL sponsored FDP event.
So it is now 11:20. By 11:30, our session will be started. So please we are waiting our expert to be here because it is already scheduled at 11:30. Okay, so there should not be any doubt about that. So by the time we will start. In the meantime, our other participants are also joining the session. Professor P.K. Jain from IITM Jabalpur, one of the best expert here at Jabalpur in the domain of 3D printing, additive manufacturing, 4D printing, and its aspects in the domain of Industry 4.0. So it will be discussed thoroughly. So please be here and just wait. Please. Thank you.
केवायसी ऍक्टिव्हेशन, वीज पुरवठा खंडित होणे, केवायसी अपडेट किंवा कोणी नातेवाईक आजारी आहे किंवा त्यांना अटक झाली
குளிக்கல நைனா
कैसे नाम दे रहे
ये अपने आप
यहाँ से चल रहा है
2%
सर की लाइट बंद कर दिया सर ये भी है ना सर
Yeah, so very good morning, every participants being here. Very good morning to all. So I'm happy to share that our session expert, Professor P.K. Jensen, has already joined us. And so we are blessed to have you here during this session.
Good morning, everyone.
Yes, a very good morning. So, dear all, before requesting Professor Jensen to start his discussion and session with you all, so I would like to just share some brief about Professor P.K. Jensen with you all. Professor P.K. Jain is currently working as a full professor in the Department of Mechanical Engineering at IITDM Jabalpur, Madhya Pradesh, India. He obtained his PhD degree from IIT Delhi in the area of additive manufacturing processes. He has published several research articles on the domain of part quality improvement, SLS, FDM processes in the leading international journals and peer-reviewed international conferences so far. He is currently dealing with the sponsored research projects, the development of additive subtractive integrated rapid prototyping system for improvement of part quality supported by Department of Science and Technology, India. He is also actively involved in the various research projects, patent as well in the domain of 3D printing, incremental seed forming, sponsored by BARC, Mumbai, and Imprint India. Earlier, he has served as project scientist and research associate at IIT Delhi. If we talk about his broad area of research, it include additive manufacturing, rapid prototyping, tooling, CNC machining, geometric modeling, CAD/CAM integration, human power, energy devices, nanotechnology. So far, he has also been awarded various awards at different levels, institutionally, globally, as well as at national side, and has also been honored with the various reputations. So with these words, I'm stopping myself here and requesting Professor Jensen to start discussing on the theme of this FDP. So you are welcome.
Thank you very much. Let me share my screen.
Yes, please.
So very warm good morning to all the participants. I hope now my screen is visible to you.
Yes, sir. You're audible also. Your screen is very visible. Thank you.
Fine. So sometimes there may be a little changeover from the screen to screen. I'm using multi-screen device here so that I can run the different softwares as well. So I hope one day all the participants have gone through the different additive manufacturing processes. In the session, we will briefly discuss two processes, FDM and selective laser sintering processes, and come to the MATLAB programming solutions to be applied to have some good biomedical applications of 3D printing, which is originally known as, technically you can say, known as additive manufacturing. So initially, let me begin with why we go with the additive manufacturing processes. Generally, we know any product while we go for making, we remove the material. We remove the material carefully from a stock and until we get the desired geometry. So this is what we call known as the subtractive processes, right? What happened with the subtractive process? sometimes, or even you can say many a times, the process is very when the part geometry is very complex, the process will be very, very time consuming, exhaustive, and very, very expensive, and even some parts to be very, very complex to be machines. You can see in such situation, like here, you see here the CNC milling machine going. So in this area is very difficult to reach the tool. And you know, for biomedical applications, when you talk about the human anatomy, the all the parts or surfaces are very, very complex, sculptured in nature. So reaching out to these parts is very, very difficult. Right? So removing material from these areas is very difficult. So instead of going for subtractive process, we choose to go for additive manufacturing process, where we deposit the material successively. So here you see this is the print material, and this blue color is the support material, right? So what we have, instead of subtractive, we are adding the material to a component, right? So this is what we call the additive manufacturing. And what the main advantage we got while we go for additive manufacturing, or you say 3D printing, that the complexity of part is no more a limitations. Any complex part, whatever we can imagine, whatever we can, geometric modeling can be done using any of the software that we can print. So what we say, often picture is worth 1,000 words, right? Instead of communication, you want to communicate in a word language, you would prefer to give a picture, right? Initially, that additive manufacturing 3D printing as developed as a communication tool, where people want to communicate with their team members, share their ideas, share their product with the patent office or something like. So suppose we have a picture which we call are known as a worth per 1,000 words. Now what is happening? We have a model in our hand, right? So a model is worth 1,000 pictures, right? So see over here the different pictures you can see here. The temple model you can see over here, the car model, the engine blocks, the functional springs, and here you can see the medical application, the full HUD model, the pins, etc., printed with different colors for communication purpose, right? This is the G-Carp printed model. So this is the advantage we got with the additive manufacturing processes. We can save the lot of time, we can save the lot of material. The process is very, very fast, right? So with this advantage, we go with the additive manufacturing processes. With the biomedical applications, I will be coming to the biomedical applications. Then we have the two processes. So first processes, which is most popular, easily available, and nowadays very, very economically viable and economically suitably available for you. So this is known as the fuse deposition modeling. Just like our Mehendi cone, we use two filaments. One filament for support material, this support material, one filament for part printing material, and we have this layered information, right? So everything in additive manufacturing you want to have in the layered information. So one layer, second layer, third, fourth, up to the top, right? And here we detect the overhanging surfaces. So below this overhanging surface, this support is generated, right? And in FDM process, this is done on the platform. This is a closed chamber, and two wired spools are there, the heated rollers are there, and here are the extruder head, heated nozzles. So from this, both the materials are extruded one by one on different layers. Say for example, this layer, here the support material deposited, here the part material deposited, right? And from here you can see this is how the every layer is modeled. So see how the different models you can get, different parts you can get. This is the house model, this is the big assembly for a engine model, right? Then you can see this process video as well before we move further. So two processes we are going to talk.
Starts as an STL file generated from a 3D
Can you listen the sound as well?
CAD program. The model is oriented within the computer exactly
Yes,
as
sir.
it will be built in the FDM machine. Orientation may affect build time, strength of features, and support material generation. Once the model is oriented, the software divides the model into evenly spaced planar sections, each measuring as small as a few thousandths of an inch. Supports are then generated for overhanging sections. Each layer consists exclusively of non-overlapping and non-intersecting curves. Tool paths are created in the regions, indicating whether the FDM machine should extrude model material or support material. Once the tool paths controlling the XY movements have been generated for all layers, a file is created and sent to the FDM machine. Inside the heated build envelope, the model material in filament form is heated to a less viscous state for extrusion. The model is built layer by layer from the bottom up. On each layer, the extrusion tips follow the tool paths calculated in the computer. After each layer is completed, the plate drops and a new layer is added. When the final layer is complete, the model part can be removed. After support material is removed, you are left with a strong, durable, and functional prototype.
Right, so this is what we have the FDM processes, right? Very briefly, I am going. If you have any question about the process, please type in the chat box. I can read on other device and I will discuss. Otherwise, I will keep on moving, right? So the next process, very briefly, I'm going with the SLS process so that we will be able to understand why we are talking on the programming to be done in the MATLAB or any other software package, whichever you would like for the comfort. You are good in programming. You can use Python or anything else, right? I have done a lot of programming to have my own apps, own machines to be controlled. I'm using in MATLAB. So you see here in the SLS process, what we have here in the center diagram, you see the scanner, here the galvano scanner, the laser beam and the beam expander, and here is the recoater. So two recoater on both the sides where the material is in the powder form. Remember, in FDM process, what we have the material in a solid form, wire spool polymer. Here we have the polymer material in a powder form around 40 to 60 micron size. So here two recorders and these are the infrared heaters. Right? So these infrared heaters, say for example, the sintering or you can say melting temperature around 180 degrees centigrade for this polyamide nylon 12. So what happens? Just below 4-5 degrees centigrade temperature, we heat the build platform, and remaining 4-5 degrees centigrade temperature which is required for sintering, not completely melting of the polymer material, we use this on this with the laser. So this 4-5 degrees centigrade temperature rise has been achieved with the laser beam, right? Once this solidification on the selected area, this laser beam will come on the selected areas only, like see in this figure, right? This is recoater, so recoated the powder. This layer thickness around 150 micron. Okay, with just one this layer recoated, reheated, so reaches say around 172 degrees centigrade temperature. Remaining 4-5 degrees centigrade temperature rise occurs because with this laser beam. So only in the selected part, selected area, the laser beam occurs and the part solidified. Once it is solidified, this entire platform will go down. Once this platform will go down, right, you can see this selected area. Now this recoater will again recoat the new layer, right? So your system will be ready for next layer. Then this cycle will keep on continue until the full part is fabricated, right? So look at this one small video. Okay, let it be in this screen itself.
next school khair
You can see over here, this is the powder bed and the tensile specimens are fabricated. So just because we have conducted this experiment with nanoclay, so we can say some reflection of the laser beam while it is coming on the polymer material, we can see, otherwise it is fully absorbed. The laser heat is absorbed by the polymer material, and here you can see this solidification is done. Both the sides you will see the recoters, right? So recoter will spread the powder and the light will be switched on, that is the infrared heaters, to keep the entire build chamber just 4-5 degrees centigrade below the melting temperature of the polymer. See this is the recoter. See, this is the recoter spreading the new layer on the pre-built part. So platform going every time downside, and you see here what happens in the FDM process. You require the support for overhanging features, but in the SLS process you don't require the support, because the unsintered powder available on this part bed will provide the support to the overhanging features like this here, right? So this is the unsintered powder and this is the solidified powder, and this is supported by this unsintered powder material, right? So you don't require any additional support structure to be created in case of SLS process. Now see which kind of parts you can build over here. Hollow space with two different material. Okay, to create hollow space with two different materials. Are you talking about two different materials or two different layers? Okay, I will just take you type your questions. Keep on typing the questions. Very good. So I will take up together, right? See, the different parts are built like this. The car seat build, this is broken into the different small parts and one built and then reassembled. Okay, now see, this process is already extended to the metal additive manufacturing processes where 20 micron size stainless steel powder has been used. Now see, otherwise how much uh, different components of the die you required before you do the casting for this part. No parting, no single parting line, a parting surface would be sufficient. More than 20 parting surfaces would be there, and you have to assemble the die, do for the casting, and then remove the die. See, similarly in this, how many parts this component have. So the machining is almost impossible, and going for forgings and castings very difficult to create a die, right? Every time the investment casting. But when you go for additive manufacturing processes, that you can easily create. You can see over here, this is the using with additive manufacturing, such metal components can be can be done. Now look at this. I'm coming back. First I have covered the processes. Now I'm coming back to the process chain. You see here what we have to do. The creation of geometric model. You can do with ProE, CATIA or any other software, whatever you would like. Then you have the tessellation, right? What is tessellation? Anybody have any idea? You can type in the chat box. So see here, this is the tessellation. You have a spherical ball, and this spherical ball is converted into the piecewise approximation of the surfaces, right? So everywhere the surfaces is the planar surface like this, right? And once we take the minimum side surface, so that we reach to the triangle, right? So once we have it is in a triangle, we call it the STL file, standard triangulation language, right? And then we do the slicing. So what happens, this tessellation only facilitate the slicing processes, because this surface, otherwise it will be very, very difficult to have this surface cross section is calculated, right? So see, look at this, the one cylinder, you have another cylinder. Can you identify the difference? This cylinder is cylindrical surface, and here it is a tessellation. So you see everything is now converted into the planar section, and just you want it has to be mentioned in a triangle, right? Standard triangulation languages. So that's why everything is now measured in the kept in a triangle, right? So what happens now, the intersection of this surface, this finally you are going to get a circle, but this may n number of side polygon, right? So you have approximated the surface, you are getting an approximate contour in terms of polygon instead of a circle. So that tessellation allow you to go for the help you to find out the slicing, right? Once you do the slicing, you require to get the slicing. After that, either the nozzle path, depending on the technique. If it is a FDM process, then you require a nozzle path, and if it is a SLS process, then you generate the rotation of galvano scanner to find out the this laser scanning path. Once you have the laser scanning path, then you have the you can print the part, you can make the fabrication of the part on RP system, right? Then you go for post processing, cleaning, etc., finishing, etc. Then after finishing, you can check whether the prototype is correct or not. If not, then you have to make some modification in the model, right? So you have to do the post processing, okay, so to have the final better finished product in your hand. This is the process chain we follow. Okay, so starting with the geometric model, tessellation, slicing, nozzle path generation, then part fabrication, and the post processing to be done over here. Right now, let me show you how we are going to implement this entire process. Many of you are aware about many open source softwares or some high cost software like Magix, Mimix to repair the STL files, and after repairing of STL file, then do the slicing, generation of the nozzle path, etc. Okay. So look at this. This is the ProE model, right? We have created in a software ProE. You can create it CATIA, AutoCAD or anything. Now you coming to the second file. Can you notice this file have contains all can you notice the entire file? Yes, meshing kind of thing you can say, but only here are the triangles. Yes, the tessellation is similar, you can say the meshing, but here only the triangles are there. And the important thing you notice here, where is the planar surface, only two triangles are sufficient. Here you see the circular surface you are getting. So the size of the triangle is very, very small, so that you should not lose the intent of the designer, or you can better approximate the curved surfaces. right? So here the triangle is small. You can have more smaller number of triangle, but what happens if you have the more smaller number of small number of triangle, the number of triangle in the file will be increasing, and hence it will increase the complexity of the file, because next you have to calculate the intersection, right? So you see on this top surface you will find only 2 triangle are sufficient. Here 2 triangle are sufficient. Here in between one edge is coming, so more than 2, 3, 4 triangles are there, right? So this is how you have the triangles, right? Now look at in this slide. Can you notice here what this blue color points are showing? You can notice over here there is a green color plane. Okay, with this green color plane we are just calculating intersection of this all STL file. So here this STL file is converted into the triangular surfaces. Now in this diagram you can see the red color triangular lines only, right? And the blue color dots are showing the intersection points. So you can notice over here this black color contour we will talk little later. You see here intersection point, this is another intersection point, this is another intersection point, and these intersection points we have to calculate, right? So mathematically what is happening, you are finding a plane. Yeah, we generally what happens if we talk about the tessellation, we can take any polygon. I will show you. Very good question. You please keep me remind towards the end of the session. We are developing a new STL file. So where, because in STL file this is already a de facto standard. So every vendor manufacturer they use the triangle, right? So if it comes to STL file, we have to use only triangles, but we are working on higher order polygons. I will show you in the MATLAB. We are removing redundant data from the STL. Okay. In this session, I have not included much on the STL file, but if time permits, I will go back to talk to more on STL file. Thank you for your interest. Look at this. So these triangles, the blue color dots, we are finding out the intersection points, right? Now look at this. If we plot all these blue color points, we are going to receive this. See, this information is not at all useful for us because the random triangles are in there in the file and we are just calculating the intersection point and just we are plotting, right? Here what we want a exact contour. Suppose we intersecting at this 8, height is 8, so we want this intersection, right? We will get this in external contour, this internal contour, this contour like this. So see here, this information we need to transfer into this form, right? And what is happening here, you can see here from this point we have identified this as a contour, right? This is another contour. Got it? So you see here, this is the external contour, blue color. This is the internal contour, dotted line, red color. This is the internal contour, right? There is a clear-cut directives, methodologies, algorithm in the CAD applications, how to write the information of an external contour, how to write the information of an internal contour, right? Now the next step, what we discussed, we have to generate the nozzle path. Now remember why I am talking all this process, because when you go for a medical application, you have to require a contour information to be for 3D print. Basic requirement for any 3D printing machine, you should give the information in a contour information. Contour information means slicing, right? So you have to do this slicing every Z height. Once you do this slicing, the information you have to supply to the machine to generate for the nozzle path like this, right? Now see, the next step is to go for the nozzle path. For generating the nozzle path, say for example your nozzle is starting from here. So what happens? It has to deposit the material in this area, stop over here, then start depositing material over here. Say for example your nozzle is starting from say here. What is required? It has to deposit the material in this area, no material in this area, then again deposit material in this area, no material in this area, then again deposit over here, right? So means this portion has to be solidified, right? Clear? So you can make an algorithm kind of thing when this nozzle passes through this, or your laser path passes through this first contour, right? So your material deposition will start here, your material deposition will stop, then again your material deposition will start, then again your material deposition will stop, then again material deposition will stop, right? So in this way you are going to develop your tool path, nozzle path, or the laser scanning path. See in this next page. Now look at this. Once you develop this nozzle path, what it is showing? Here, no material deposition, right? Material deposition only in this pink color. Got it? Right? So this is the area to be laser scanned on the part layer, so that it will become solid and the remaining material on the same layer will remain unsolidified, right? This is the way you are going to do that. Now look at this, how we do this. Say for example, I am taking you the magic software. Anybody aware about the magic software? Please type in the chat box yes, or else I will take you to the software screen. So okay, look at this. This is the magic software screen. Let me move to the magic software directly so that I can show you. I hope you can see the software screen. See, this is the part. I think somebody was asking how we have to create the difference between two parts, right? Two layers, right? Two parts. So look at this. This part have the three spheres. You can see here inside there is a hole, right? So you can notice there are three spheres, one inside each other, and they are not touching each one, right? So how you see, we have seen the video for selective laser sintering processes. If we go like this, see here, we will start from the bottom. So this will be the part, right? The first layer, second layer, third layer, fourth layer. On this layer only this circle, right? On this layer only this spring. That means where the red color contour is showing, blue color contour inside surface is red, right? So you can notice that at particular point this much area only be solidified, right? So this contour information you are going to supply to the machine, right? This is the software doing for you, and in the previous slide I have shown you how we can do it by our own programming skills, right? You can use the MATLAB like this. This software I am showing, this is a paid software. You can do the similar thing with the open source software also, but they do not have many facilities like this. Okay, so look at this. At this stage, at this height, first sphere will start solidification, right? Now let me move little bit further. You see, four contours are there. You see here the four contour red color contours you can see over here, right? See, the four contours are there like this, right? So here in the red color area only the solidification, the laser will come into on this area, right? And the remaining area will be provided support by the unsintered powder. Okay, now look at this. If I move further, you see the second sphere start building, and there is no connection between both the surfaces, right? Second sphere appears just like it in the space, not touching with not touching with the previous sphere, right? But they will be built. So what happens, the unsintered powder in between both the spheres will be provide the support. Look at this like this. I'm moving like this. Second sphere. Now you see third sphere coming into picture, right? This is the third sphere coming into picture, right? So this way we continue in the actual building, right? This is in the software third sphere. Like look at this, third sphere is about to complete. Sphere is complete, and first second is still going on, and in between of these three spheres, unsintered powder is there, right? That unsintered powder will be trapped inside. In the design of the part itself, there are holes. So what will they? They will be provide the support each other, right? And the unsintered powder will be removed. So the part will be built with a single, without joint, without any assembly, right? Look at this. Let me move further. Look at this. So this is the sectional view I have shown you. Now look at this. Let me show you the triangle. Can you see here the lot of triangles are there on this part? Now look at this. The entire surface is now triangulated. This triangulation we can do with the STL file, and the lot of errors can be there. Now next I am talking on the different errors going on in this part. Let me take, and you see if I go for the sectional view as well in this mode. So look at this here, the sectional view is there. Now look at this. These triangles are there. These are the cross section. When these triangles are cross section, you will find that these contour points are connected each other to make a closed contour, right? So here at this level, you can see the 4 contours are there. Like if you go more bottom, you can see here the only one contour. This contour you can see, right? So from these intersection point, these triangle points, you are connecting them, and you are creating a contour information, then generating the nozzle path. Okay, let me go back. At this moment, I am not taking any other feature of the software. Okay, and then we will go. Right, so this is the way we have done the slicing, or you can say the STL file repair, etc. we can do with this magic software, right? Now you can do a lot of manipulation, you can cut the part, you can write the text, engrave many things. Okay, okay, now we will come to the MATLAB part. You see, we can open this STL file into the MATLAB, we can see the manipulation of the file, we can repair the file. Okay, so look at this. Have you anybody open the STL file in the notepad? Are anybody working with the STL file? Type yes or no in the chat box. You can see on your screen the STL file exported, one from the left side you can see from the SolidWorks. Right, this we have SolidWorks or AutoCAD we have exported, and this is from the Magic software. Okay, so this is the STL file, standard triangulated, and how the information is written. You can see over here, facet normal, outer loop, one vertex, second vertex, third vertex, right? Here the unit is in the scientific unit. Here is the decimal unit. So you see over here the solid, the facet normal. This is the facet normal in the STL file. This is the outer loop. So first vertex means x1, y1, z1, right? This is the triangle. So this is the first vertex, second vertex, and third vertex. So xyz for first vertex, right? And the same for second and same for third. And this is the surface normal. So cx, cy direction cosines in 3 directions for this surface normal, right? So you can have this file, and how it look like this. For example, let me open this file. See here, this is the, if we are using the cube file over here, can you notice how many paragraph should be here in this file? Anybody? How many facets the cube will have? How many faces normally cube have? The 6 facets cube have, right? So every facet is now represented as a triangle. So how many total facets would be there? Yeah, Deepak, correct. 6 would be in a normal case. But when we save the cube as a STL file, everything will be in triangle. So there would be 12 triangle. Okay, now look at this. This is the file you are looking. Yeah, 6 into 2. You see, this is the paragraph. You can see there are 12 paragraphs. Every paragraph, say for example, here facet normal, outer loop, end facet. This will be the content in the file it will have, right? So this is the way how the STL file, right? In this way, there is scientific unit, and in this way, if I open this as well, see here, this is in the decimal places. So you remember how a file is written by any of the software package, right? That we have to understand. Suppose we have exported this file from the AutoCAD or SolidWorks, is a structure like that, and it is from Magic Circuitia, it will be like this, right? So see here, what I have done, I have taken 0 at center point. So everywhere the unit size is 10, cube size is 10. So what is happening? 5 minus 5 minus 5, like this, everywhere this data is coming, right? Similarly, if I take in this case when corner at 0 and here center is 0. So you see the points are 5 minus 5 and here 10, 0, 10 everywhere, right? The cube is like this. Okay. Okay. So here we have taken this is as a 0. So everywhere the value is 0 and 10, 0 and 10, right? And here what happens? We have taken for this figure, we have taken 0, like center is at here. So everywhere 5 minus 5 like this is happening. Okay. So this is the how the STL file is done, right? Now let me take you to the MATLAB. Let me open a read file. Okay, one program, right? You can see on your screen. Please type in the chat box. Yeah, okay. What is the use of STL file? STL file is a standard triangulated file, because in your STL file, what is required? Okay, let me go back. See what is our principle. Principle in the case of rapid prototyping, you want this cross section, right? How to get this cross section? This cross section would be available by intersecting. So if you take this typical surface and calculate the intersection, it is very difficult to get the intersection. So what we do the triangulation, or we export this file as a STL file. What is STL file? Is a triangulation, right? So that's why we take the STL file, which is facilitate the calculation of a triangle. I will be coming little later on that again, okay? We will be coming little later, right? I have explained you, here is the triangle is there, here is the plane. So getting an intersection with a line and the plane is very easy. Okay, you can have lot of softwares available to get the STL file. You can just any open source software or any cloud-based application or something, you can generate your geometric model, upload and get the STL file. Try to open and see it in the notepad, how it look like, right? Let me go back to the MATLAB. See here, a small program. I hope everybody has done this C++ programming or MATLAB programming. We are just reading the text file from this MATLAB. Okay, so solid one, yeah, cube. That the cube I have shown you. Let me open a cube. Now look at this. This is the cube file you have. This cube file we have opened into the MATLAB, and this is the same cube file we have shown you on the PPT. Right? See over here, this is 0, 0, and this is the 50 side cube. right? This is read. So everywhere it is now triangle. Now look at this in the command prompt. Every information this was available in the text file has been read in the MATLAB application. And you see here 12 triangles was there. So here you see faces we have identified, PTF1, this is the normal, and this is the XYZ of the second coordinate, XYZ of the third, and 1, 2, 3 up to the 12. Means whatever the facets available in the STL file, they are now available to you in a mathematical form. Okay, with this mathematical form, you can calculate the intersection. Okay, so let's further, then we will come back. Right, this is the STL file we have chosen. You see the how the text will look like. Okay, with this text file, we have going to calculate the intersection. Right now, point is here. I think let me skip the missing part. Otherwise, we would lose the most. Okay, 45 minutes we have. Right. Many cases, what happens? These STL file have the errors. Means suppose we delete or by mistake our software capability is not able to generate the complete closed volume. STL file should be a closed volume. Look at this. So this will be the surface where the high curvature change occurs. This triangle is not generated. Say by this application. See, this is the top surface. STL generated triangles you can see over here, right? These triangles. Okay, but here what happens? This is triangle, but this triangle is, there is a mathematical algorithms are there. The tolerance limit are to be set. If tolerance limit is more than this, the software will not generate the triangle for this portion. What happens? This will be a hole, or you call it puncture, right? So when you go for a slicing process, you cannot generate the slice for a STL file which is containing the hole. So look at that. You have to ensure that your model should not be having any such error. Otherwise, your machine will not be able to fit the part. Okay, look at this. You have to create a valid model. What we call it the valid model? No facing facet, no degenerate facet, no overlapping facet, or any other abnormality, right? We are not going into detail at this moment of the different errors and how to repair them. We are just finding it valid model. Valid model means no hole. You see over this model is correct. All sides are covered. So what is our step? Go for the slicing. Slicing will be generated just like biscuit packet or bread packet. You can see the different slices are there. Then now the next step, for each and every slide you have to generate this nozzle path. Okay. So this will be the third step you are going to generate with the nozzle path. Okay. Now see, if you have an invalid model, look at this. Here two facets are missing. So what we call it gap. Okay. Once you have this gap and you go for the slicing. So what happened with this gap? You calculate this contour, and since because in this portion you don't have any triangular facet, right? So what will happen? Your contour will be look like this only. This contour is not at all closed. Okay. Now you are going to generate the nozzle path. So if you generate the nozzle path, what will happen in this area? When you come over here, it is going to infine. Your nozzle will not come back. Right, there is nothing to obstruct the nozzle path, or you will not have the closed contour. I hope this point is clear. If any missing facets is there, you will not be able to generate the nozzle path. So what you can do, you have to repair this STL file, right? Then there are algorithms, methods to then you need to generate this, right? So say for example, this is a gap, then you need to generate the different triangles, identification of this gap, right? This gap is now again subdivided into the triangles in this way. And these many triangles are written back into the STL file, like first triangle, second triangle, third triangle, fourth triangle, and they will be written into the STL file. I will show you how to implement this in the MATLAB program. Okay. See, that is what I have told you to get the intersection. Let me first go to the MATLAB, then we will come back again. See this small program I am showing you to get the STL. So we have taken this STL. Okay. Can you notice here? One facet is missing. If you are allowed to unmute, you can talk. And can you see, notice how many facets are missing here in this? See, the inside triangles are visible. You see, this facet is missing. Yeah. Right? Now this program we have written to repair, to identify which facet is missing and to fill that hole, right? You see the typical programming, you can see over a lot of conditions to be checked. Okay. And this program we have to take. So press 0 to fill the, okay, so fill the. Now look at this, what happened? This hole is filled. And just like any commercial software package, this will take it to the file. So if we do not want to change any further contour, we will type 2 to generate the STL file and press enter to have the file. So KKR, let me write, and then we can, you see here in the side panel, right? There is no KKR file available in the left hand side current folder. Okay. Now once I say please enter the file name KKR, the new STL file is generated. Here, look at this KKR. Once we open this KKR file, you see here the way STL file was written, so it is generated. Got it? This is the way STL file is generated. Now even if I run once again, you see here, let me take another file which two missing facets. See over here. Can you notice here the two facets are missing? Okay, so here two facets are missing, right? Now let me fill this. Those who are interested in such kind of programming for STL file or repair, they can talk to Dr. Ravi Kumar, and we can have more detail about those programming techniques. Right? Looking that, see this figure. File is now closed, but the orientation is not correct. Remember, we have not talked much on the STL file rules. There are certain very specific rules to be followed by the STL file, right? So that we can repair, we can slice it further. Okay. Now look at this. Now we need to change the orientation. Okay. Let me go back and change the orientation. So we have changed the orientation. Now look at this. This edge is coming on the top. Your cube is remain there, and none of the normal to the surfaces intersecting each one. So by this, you see, we have closed this cube, and now we can go further step for the slicing. Okay, so now we can write over here the new file like KKR 1. Sorry. The file name is kkr2. And you see the new file kkr2 is created, kk2. And you open it, you see here, this is the new file. New STL file is generated, which is corrected, right? Now there is no hole, nothing like that. Okay. So we can move. Now the next step is to generate the nozzle path, right? So for nozzle path generation, let me open another file. Okay, right? Then we go for first for the slicing, and then we will generate the nozzle path. Okay, so let me take you back to the and then we will see. Ananda, in one lecture, if urgent, 1 o'clock, yeah. Sorry. So this you have taken for the STL repair, right? Now see how we go. Somebody was asking for how to use for the what is the use of STL file. You see, this is the use of STL file. This geometric model is now converted into the triangles. Look at this exploded view, and every triangle is kept as separately. Okay, this is the use for STL, use of STL file going for slicing. Now in this way, what you can do, you can have the file. Okay, so now you can easily calculate the triangles, right? Now you see here, this is the contour information you are going to get here, right? Here one simple triangle, right? This triangle, okay? And now in triangle, when this plane will intersect, you will see, you will find this point and this point. Next triangle, these 2 points. Next triangle, these 2 points. But what is the difficulty in that? The triangle are not in a sequence. So you have to arrange them in a sequence, right? Okay. So after this classing, you can see over here, right? This you can find out that intersection point, and this contour will be available to you. So you got the point, the advantage of getting the STL file, right? And what we do in programming also, you can separate out one triangle, find out the intersection of this one triangle, and then you can generate have a for loop, and then for loop you can get the intersection of multiple triangles, right? Look at this triangle. Let me show you this again in the MATLAB. So this is one triangle, right? Then you can make a file, a program which can help you to get the multiple triangles, and then you need another program to arrange them in a logical sequence, right? See here, this is the cube we have taken, and this plane is intersected at z equal to 25. Okay, so these will be the intersection point. Got it? Right? With these intersection points, you will see, you will find out the intersection point and then arrange them in a logical sequence like P1, P2, P3, P4, P5, P6, P7, right? Then you need to find out the contour information. How to find out? You see here, this is the first point on your line. 0, 25 going to 0, 0. Okay. So what we will do, we will find out this 0, 0 where this available in this tail matrix. means start point, end point, start point, end point. And you see in every triangle what is going to happen, wherever you will find this connecting point, this point and this point is same. This point will come along this triangle, this point will come along this triangle. So for this triangle, this will be the end point, and the same point will be as a start point in the next triangle. Okay. Now look at this. Okay, so see, we will have this, and then we will find it out in this way. So 0 0 connected to 0 0, so means first segment will be connected with segment number 8 going 25. Then you will find this 25, so this will be connected with the statement number 4. Got it? In this way you are proceeding. So you see here the first segment connected with 8 segment, 8th is connected with the 4. In this sequence your segments are connected. So you will get this contour information. Okay. Then you see here, I am just showing you the pyramid. So you see here, STL file intersected, 4 points are found out, and the contour is formed P1, P2, P3. Got it? And then by this way, you will do the intersection at each and every layer, and you will find this contour information for successive to all layers in case of pyramid. Got it? Then we write this all information into the CLI file. Let me skip the CLI file at this moment, coming to directly to the nozzle path. Before this nozzle path, then suppose this is the blue color contour you find. Okay. In this contour, you will set the parameter for 3D printing and generate this nozzle path. And this nozzle path has to be provided to your 3D printing machine in a form of G code and M code. Right? I hope you remember this G code, M code you also use for the CNC machining. Same G code we will use for the 3D printer, right? And this all information is written into a text file, which you can directly send it to the 3D printing machine. Okay, let me take you again to the MATLAB. Let me close all this. Okay. Let me open a file. Now I am opening a STL file in this program. So since we are talking on cube, let us take a cube. Okay, and this cube. See here, the program is already knowing its minimum Z is 0 and the maximum Z is 50. So let me put the height, say 34. Now see, this is the STL file in the first sheet. See in the first figure, this figure. This is the STL file. Okay. Now look at this second file, which I have already shown you in the PPT. You have find out the different contours, different intersection points, right? This file. Okay, you got the different contour points. Okay, now in the third file, you can see here, you have find out the contour, the black color contour you can see, right? This contour we will send to the next program, which will generate the nozzle path and save the program in G&M code. Okay, let me close all these three files first, And you see here in the side panel, we have the G code and M code file, right? I'm deleting this file so that the next program will automatically generate this file. Right? You can see the blue color I have highlighted here in the side panel. I think there is some time lag. Okay. So see here G and M code file, I have deleted this file. Okay. Now I'm opening this nozzle path. Okay. And you see here this MATLAB program I am running, it will read the data from this data in data XLS file, right? Any of you know the MATLAB programming? Say yes or no on the chat box. Okay, one yes. At least 10 responses quickly. 2 yes. Okay, good. Good to know. 3 yes. Oh, mixed kind. You see here I am using this information where we have written the data in the previous program. Now I am reading this. XLS reads data. Right? We are reading this data file where all the contour points are saved. Okay. Now let me run this program. So the nozzle path is executed. Now it is asking me for the input size, say 5. Asking for temperature, which bed needed to be heated initially. Let me say 230. And the temperature at which nozzle needed to be heated initially, let me say 240. Okay. And then now you see this is the tool path generated by the, right? So this is the red color, the tool path generation you can see on your screen. Okay. Now this tool path is again automatically this program is writing into the GM code. Let me take you to that location. See over here, we have using this fprintf file ID. Notice I have just selected this text. Okay, so what happening, whatever the information we have calculated, collected this information in this structure, you can see G and M code for 3D printer nozzle path. We are opening a file gcode.mcode.txt in write mode, right? All this information we are writing, and this is fprintf. So whatever the calculation we have done, the entire calculation into the written into the G code file. Got it? Now look at this. Let me open this G code M file. Okay, you see this file you have generated from your own MATLAB program. This file you can directly send to a 3D printing machine. Got it? Okay, now I think we have done enough in a MATLAB. Let me switch over to PPT and take you some more interesting applications. So this up to this part, if you have any question, please keep on typing. Okay. Now look at this. Okay, CLI file. Let me leave it. Right. Now we are coming to some more applications. We have just skipped the CLI file contour information, which is required to be given to the machine. Okay. Now see the one example I am showing you here for medical applications. Look at this side here, just behind this human ear. This side, this is the temporal bone, right? And doctors need to perform the dissection on this temporal bone. The problem with this temporal bone is that it is very life of this bone is very less. Means the death of a human, this bone is dissolved very quickly in the body, right? So generally doctors don't get this human for the dissection purpose, right? So this temporal bone, this red color area, you can identify this simulation video we have captured from the Mimics software, right? Mimics software take your CT scan, MRI images and convert them into a solid model. and that solid model you can export in a form of STL file. Okay, so see this temporal bone we can generate, and we require to have an accurate geometric model of this temporal bone. We can develop it using Mimic software, and the 3D printing to be done with the closed tolerances, right? And also the further you have to make use of the material or composite materials or whatever any other material you can mix. You can have a combination of 2-3 materials, so that the properties of the bone are close to the means properties of the printed bone close to the actual bone, so that doctors can perform this detection, right? We are performing some rehearsal operation on this. Okay, so for this rehearsal operation, you see here over this, right? So that the material properties, if not very close to the bone, doctors cannot perform the rehearsal. They cannot have the feel of working on the actual bone, right? Now look at this. See, you can do this exercise. You can see this is the first image I'm showing you, right? I will show it again. This is the CT scan. You can find the different grades of the color or shades, you can say, right? Technically, we have the Hounsfield values. Okay, so based on Hounsfield value, we separate out this. Okay, let me take you first this. Based on the Hounsfield values, you will separate out where is the skull, where is the tissues, right? Where is the blood, right? So based on this, and you can see here that the more I'm zooming here, you have to do a lot of image processing techniques to separate out these contours, right? These contours are separate out. Till now, you know, for 3D printing, what is required? You require this kind of 2D contour. Okay, so you need to separate out these 2D contours, maybe in commercial software, or maybe you can develop your own technique in programming for research work. Okay, now look at this. This is the 3D displaying contour slides. These slides also you can take up to the MATLAB and you can perform this rendering part. So you see here from CT scan, MRI images, you have this. These images you have converted into that for simulation models, right? Now let me go back. See over here, this we can utilize for creating such model. You can see here, this is the FDM printed skull model, right? Then lot of CAD operations, we have find out what is the size of the implant, right? You can see here, this is the acrylic implant size, measurement is done all. And you see here, this patient, after the accident, the bone is completely fractured. So there is no bone available to support the eye transplantation or the artificial eye. So you see, this is the artificial eye, but there is no support. So a lot of rehearsal has been done. The surgery time has been reduced from weeks to days. And then after the eye implant, right? This is one, the temporal bone I have talked in to you the previous slide. Okay, so you see, this is the 3D printed bone and this is the actual bone, right? And this is the Mimics software screen where you can import all these CT scan images you see here, and this is the STL file you can get by separating based on the on-speed values. Okay. See, further this 3D printing will allow you to go for this kind of facial reconstruction. You see here, doctors has to perform a lot of surgery to get this facial disorder to be again brought into the shape. So you see over here, this is the lot of planning is required, and these 3D printed models you can generate based on the CT scan and MRI images. Look at this. This is again the shape deformity. You can see over here, this portion, right? Another portion you can see over the same figure is there. This is the rendered view, and this is the only the skull model. Okay. See, So these facial reconstructions you can do for printing, etc. You require the programming. Otherwise, these softwares are very costly. Maybe one seat for one software is around more than 20 lakh rupees. Okay. See here, another example I'm showing you. Design and fabrication of a mandible, right? You go see here the lot of tobacco, gutka chewing. This tumor is visible in this, right? You can see over here, this tumor is there, right? So for doctors to perform a lot of rehearsal to how to change from where to cut this bone, replace with some other bone to be brought from the body, right? So we import this data into the Magic software. We have created this mandibular in a physical model and the 3D printed model of the mandible implant we fabricate with the CT scan images, right? And then we have to find out, separate out from the skull. And then we have to 3D print, take care of the mechanical properties, and the lot of CAD operations. You see here, this is the Magic screen, right? So the three side are mechanically, you can say front view, top view, and side view are exterior, posterior in medical terms. And this is the complete model of the scale, right? This mandible from this area, this has to be separate out from here, this portion. And here, this portion, you can find out the tumor. Right, this portion, the tumor, you will find out. Okay, so based on this, then you have to do for further. So the preparation for a skull model, we will cut down half portion, we will mirror this image onto this side. So we have cut down over here, we have mirrored it. Okay, then now look at this. After mirroring, we have to do lot of STL repair, etc. And then we have created this. Okay, so see over here, this all operations to be done for medical applications using the 3D printing. Now see another work done by a PhD student. See, this is in the guided endodontics. So finding optimum direction for root canal treatment. I hope everybody is aware about the root canal treatment. Doctors mostly rely on the 2D X-ray images, right? So from CBCT scan, find out this 3D and the 3D contour for this tooth model, right? This is the tooth model and this is the STL file generated from the Mimic software. Okay, based on this Mimic software, you see this one contour, external contour, internal. So we can find out the center of one contour and then we can find out center of all the contours. Okay. Then based on this tooth you can see over here, this direction has been identified, right? Once this direction is known, to perform root canal on this tooth, what we have to do, what we have done, right? We have built this STL model. This is the guide model, or you can say surgical file model. And then we have created this kind of jig, CAD model of the jig, right? This is 3D printed and this is the original tooth. right? So based on this, we will fit into this, and then we will perform lot of operations, and then this is the validation. You see here, this is the bottom side, this is the actual teeth, extracted teeth, okay? And on this is the jig fixes, like this. So this is the tooth model, and this is the jig fixes, and this is the hole in which the tooth has to be, this has to be created. So here you see in this jig model, the pre-drilled holes are there, right? So doctor know in which direction they have to make a file. Okay. So this is one another validate the work for the guided endodontics. Okay. Another interesting part for medical image processing we have taken up. As we know that RGB images can be converted to grayscale, then the point cloud, then image to STL. So what we have done over here, see, this is the RGB image. This is converted to grayscale, and grayscale 0 to 255, right? So this 0 to 255, any value at particular color is converted to the third dimension. So we have given, based on this grayscale value, the height we have given. Okay. So based on this height, right? Based on this height, we have chosen the top part to be printed, right? Okay. Now look at this, the actual implementation. You see, this is the RGB image. This is the RGB grayscale image. This is image to STL file converter. This is the nozzle path. And these are the actual printed image. Okay. So, okay, let me show you the image. Can you see the image on my mobile, my camera video? Can you see? This is the 3D printed image you can see. Okay. So this is the image you can see over here. And this is the way how you are going to generate the images using 3D printing, right? So we would like to close this session. If you have any questions at this moment, please ask, or else I will just let you show how we have done the 3D printing on our CNC machine, right? So see over here, we have a Ukuma CNC machine. Okay. So this is the Okuma CNC machine we have, on which we have developed a extruder head. You can see over here, this is the extruder head, and this same extruder head is shown in the enlarged view. The resistance heater is there. So on the same build platform, we will print the model. हाँ सर, मैं ऑफिस में ही हूँ सर, एक ऑनलाइन लेक्चर चल रहा था. 5 मिनट, 5 मिनट. ठीक, हाँ. So look at this. Let me show you this machining video first. Can you see on your screen the machining? The deposition is done. This is on the CNC machine. right? So this is one, the deposition we take place, right? Let me to show you another one more video before we jump into the question. On the same setup, look at this. On the same setup, the CNC machine is removing the material. Okay. Right, so this is on the same setup. You can print your part, you can machine your part for better surface finish, right? Let me cut over here, and you can see over here also, this is working in a STL5 mode. See here, the triangles are generated on top. Okay, due to short of time, let me stop over here. The flexible part, the electronic circuit printing part, I'm not going into that. The aluminum printing, we are just recently working, so I'm not going into that as well. This is our aluminum printer. You can see over here, just like your 3D printing machine, this is the in-house developed machine which is printing the aluminum. Right. So let me close this, and I just permit something more. And this is what we are looking for the future of 3D printing. You can see the body part on your screen, right? So this is the future perspective with 3D printing. And let me close this session and let us open. I think analyzers may unmute for your questions. Got it's polymer based. Yeah, Dr. Pandey. Any polymer which have tendency to be joined together, we can use, and that is in the pellet form. So there is no issue with what size of the wire we have. Any size of the pellet we can have depending on our nozzle, right? So this will be printed. Okay. Which type of software required to converting X-ray image to? This is the Mimics software I have shown you. Mimics, the materialized Mimics website you can open and you can find out the software. Let me show you. You see the first part, the first slide, right? You see, this is the materialized website, and you can find a lot of things over here for healthcare, and including the 3D printing, orthopedic, craniomaxillofacial, right? Materialized, mimics, fit shoots, many software you can find, right? Lot of things like I was talking about. You can see this picture, right? And you can see this jaw is broken from the both the sides, right? So TMJ surgery, precision solutions, right? Tumor effect, many things you will find, right? On this website you can go and you can find lot many things. And these are the developer of the Magix and Mimic software. Okay. Yeah, only in triangle, because triangle is the simplest plane, you can say. What is the minimum size plane is required? That is the triangle. And if you use any other, you may not be able to reach to the close to the volume, right? So triangle will give you the best approximation for a surface. If you choose a rectangle, pentagon, or hexagon, you will not be able to find out, right? You will not be able to reach to the exact surface of the geometry. What kind of research can be done in art? A lot of things are there. You just go through this website, you will find many softwares and research openings. How Material Studio will help for this type? I think Material Studio, you are talking about some software, right? Anybody else? Why we tessellate? Okay, we talked on. Got it's polymer based. Okay. What type of material is for root canal treatment? it will be created in 3D print. You see, many dentists now even they have their own 3D printing setup. Even in Jabalpur itself, they are printing the tooth aligners. JPEG and JPG files into STL format, right? Mimic software you can use, right? Praveen Kumar, okay. You can use, and JPEG and JPG directly not taken, but you can see what type of files can be imported by the mimics. When I done this, JPEG was not available, so the BMP file is imported by the mimic software. Mimic software can deal with BMP. DICOM images generally it takes. CT scan and MRI data is in the DICOM format. Okay, but here you can use the BMP. Even though we were having a lot of problems, so we have written a MATLAB program to open a JPEG file, convert it to save it as a BMP file. Because we sometimes for some application we need to, in one experiment we require more than 200, 300 files. So we have written a MATLAB program. Okay, let me go back to the last question. Yeah, somebody has given the link for MATLAB. Very good. Okay, fine. So let us go back to the organizers and let me stop sharing. So I have stopped the sharing. Okay.
Yeah.
Hello,
Thank you
sir.
so much, sir, for this wonderful insight discussion with our participants. And I think a lot of queries you have already been responded during the talk also. So if you permit, sir, one or two query we can have, otherwise we can bind it up.
Yeah, please go ahead. Otherwise, I have already reading and replying.
Yeah, one query is there, I
How
think,
to
but
find this?
how to find the material or polymer useful for bioprinting technology?
So printing is okay. Bioprinting means what? You have to decide first. Who is talking? Dr. SSK. Okay, right?
No.
Any material which is suitable for bioprinting. Bioprinting means what? Like for example, I've given you one example of this root canal treatment jig printing, right? Jig we cannot put directly into the mouth. This has to be autoclave, right? So that 3D printing material will not sustain more than 100 200 degrees centigrade. Deformation will occur. So that we have to look that right now we will not jump into that the material fully. Phase change, that is what we have shown some model that is for the training purpose, right? If you go for titanium implants, you can directly print, right? You know, the tooth caps, right? How they are printed. They can also be right now 3D printed. So that depends on the titanium material, not the polymer material. Okay.
Okay, so okay, sir. I think it was the query being asked, and some interactive query and discussion already been there during the session. So thank you so much, sir, for this wonderful insight.
Okay, thank you.
Yeah. So we are highly thankful. Thank you so much, sir, for your valuable time. Thank you so much, sir. Thanks a lot.
Okay, so I will leave. And Dil, which this link is working for all the sessions?
Yeah. It is same, sir.
Okay, fine.
Okay, sir.
Fine.
Thank you so much.
Sir, I request to please share the slides, sir.
Okay, dear participants, so it was the conclusion of the session 3, means which is the first session of today's. Post-lunch session again will be held as per the schedule, means by 3 p.m. onwards. So just have break. Links of for the attendance already been shared in the chat box.